Hi, everyone. Thank you so much for joining. Today, we are going to be talking about our multi-point system, our MDE. And so our webinar is going to be about multi-point vibrometry for full field vibration measurements under non-repeatable excitation. My name is Kilian Shamba, and yeah, pleasure to go over this stuff with you. Who are we? We are Polytech, and we are a global company. Our headquarters is in Germany, in Waldbronn, Germany, but we have offices all over the world. In the United States, we have 3 offices, one in Massachusetts, one in Michigan, and one in California, which is where I am, in Southern California. The outline for today is that we're going to be talking about single point versus full field vibrometry. Then what is multi-point and why would we want to use multi-point systems? A selection guide for how we would configure a multi-point system, and then some application examples as well. So let's talk about single point versus full field LDVs. This is one of our laser Doppler vibrometers, our LDVs. And in this diagram, you can see it pointing at a device under test. The device might be vibrating in and out of plane, and the system is able to capture the vibration via the reflected laser. So if we take a look inside of the sensor head, we'll see kind of how it works. So we have this laser source inside the head. The laser gets split. Half of the split beam stays internal to the sensor head and goes to this photodetector that we can see inside the head there. The other half of the beam leaves the sensor head, goes out of the optics, is reflected off of the surface of the vibrating object, the device under test, is scattered, and some of that light returns back into the sensor head where it is finally recombined on the photodetector with the reference signal. So looking at the change in wavelength of the between the reference signal and the returning signal, we're able to decode velocity from that. So the reason that the light is shifted in wavelength is because the vibrating object, which it reflects off of, imparts or removes energy from the laser itself. So that's the Doppler shift of light. And that's ultimately how we get velocity out of our systems. So what type of LDVs are there? So we have lots of different types for many different applications. We have out of plane, in plane, differential, rotational, even microscopic scanning as well, and 3D scanning. The most basic type would be an out of plane at the top left, an out of plane LDV. The system measures in the direction of the laser. So if you have a device and it's vibrating left to right, and you point the laser directly at it left to right, then it will measure that left to right motion in terms of velocity or displacement or even acceleration. However, if you angle the laser, then what we capture is still the velocity in the direction or displacement in the direction of the laser, but just the component of vibration on that surface. So now if we take multiple lasers with different known angles, then we can measure 2 degrees of freedom at a given point where the 2 lasers overlap, or even 3 for 3D. So 1D requires 1 head, in plane would require 2 heads, and a 3D system requires 3 heads, so 1 head per degree of freedom of measurement. So out of plane is just point a laser at an object and measure the out of plane vibration. In plane, we can measure the in plane vibration of an object using 2 heads. Differential, we can use subtraction of 2 lasers to get the differential between 2 surfaces. Rotational, we can measure a rotating object. In a microscope system, we couple the camera and the laser together through a microscope objective so that we can do measurements on things like MEMS devices, micro electromechanical systems, for things like wafer level testing, ultrasonics, different things like that. Scanning is where we have steering mirrors inside the head so that we can sequentially move from point to point across the surface and map out an entire deflection shape of the surface. And then 3D is basically take scanning and 3D and combine them. And now you have all three sensor heads that are scanning. They overlap at a given point, and then we define different points in a mesh across the surface for them to move and map out the surface in 3D. So we get a triax measurement in velocity, displacement, or acceleration at every given point across the surface of an object. So those are scanning type of systems, and the other ones are a static location. This is a single point vibrometer. So the kind of the top left first option in the previous slide. Here we can see we have the sensor head, and it will connect to a front end, and that front end connects to a computer. And then altogether, we're able to get the vibrational data from the system into our software. Or we could, of course, use a BNC output from the front of that controller that you can see into a third-party data acquisition system and take the data there. So it's pretty flexible in that way. So single measurement at a time, though. This is not scanning, so we just measure one location continuously. We get one resulting vibration spectrum or time history. So either time or FFT. And we can do a one-time, continuous, or periodic measurements. This is programmable as well, so we can, automate this in however we would want to do that. Okay, now talking about full field scanning vibrometers. The difference between the previous type and this type is, like I mentioned, that they have steering mirrors. And on the screen of that laptop, you can see an example of a result that we might get. So say that was a beam, and the beam were to vibrate, then we can map that vibration across the surface at a given frequency or over time, and then see the resulting animation as a exaggerated version of that vibration. So the steering mirrors move between all of the predefined nodes in the mesh that we created in the software to all the desired locations, and we get one time domain history or spectrum per mesh point. And then as a result, like I mentioned, we get the deflection shape or time domain response of, so we can look at kind of the resulting deflection shapes, compare them to modes, maybe if we want to, or we can also look at the time domain to see things like wave propagation through material. Okay, so kind of a more intuitive overview of how the scanning system works is that it moves point to point across the surface in sequence, across the test object. And then once that steady state, so the entire time we need to have a steady state excitation on the object or a triggered repeatable excitation, because we need some way to line all those points up so that we can see the result as if it were one, essentially one event at the very end. And that way we get a cohesive animation as a result. So yeah, we have, in terms of lateral resolution, we have micron level spatial resolution across the surface. No constraints on the size really, because we have scanning in our macroscopic vibroscan systems, as well as scanning in the microscope-based systems. And like I mentioned, we just need to have a repeatable or steady state excitation. And there's basically no limit on number of points. The spatial density can be really high if you have really complex deflection shapes or really high frequency wavelengths, short wavelengths. Limitations. So the limitations for our single point vibrometers are that, of course, by definition, we can only measure one point at a time. So we have to manually choose a point on an object, point the laser there, and that's what we measure. In contrast, the full field scanning vibrometers measure sequentially across a surface, but we have to have a repeatable or steady state excitation. So what happens if none of those conditions are true? Maybe something where we want to monitor multiple points at a time on something that's a non-repeatable event, then we would want to use a system where we have multiple single point systems together to kind of merge the two options of single point and scanning or full field and kind of get the best of both worlds between the two. Yeah. Why multi-point? So here's some examples. Yeah. Something that we might want to do is drop or shock testing. In that case, that's a non-repeatable event, and it's also possible that the part gets damaged. So repeating that multiple times won't be possible. Yeah, something even that's hard to reach, or we need to get a bunch of different angles from it. The scanning will have a hard time doing that because we have one vantage point, whereas the multi-point system will be able to get from, let's say, simultaneously the back, the front, the sides. So for time savings, that can be a benefit, as well as for measuring multiple things at the same time. Wind tunnel testing, that's inherently non-repeatable. So a multi-point system is good for that. Sensitive components as well. So if we have something kind of like the drop testing, but maybe we don't want to damage it, and exciting it too many times might cause damage. Maybe once is okay, but a bunch of times, maybe not. Then multi-point would be beneficial there. Or for something like biomedical, our bodies are not repeatable. We can't control our bodies to perfect repetition. So we may want to monitor something like, let's say, a heartbeat or different things in the body with a multi-point system. Here is an example of a setup of a multi-point system. You can see we have 8 VibraGo single point systems here, and they're all measuring together, mounted on this 80/20 fixture. And actually, I think there's even more in the back. So we have the MDE solution, the multi-point data evaluation, which is a combination of both hardware and software. So we developed some software to combine all of however many single point systems we want into one controller interface or data acquisition interface, or both. And the great thing is that we can use any single point vibrometer we want because it's agnostic to the type of LDV, Polytech LDV that we use. We can connect up to 48 sensors in this configuration. And yeah, each point can, or each sensor head can measure a different point simultaneously. And then we can control all of the sensors simultaneously as well. So if the sensors, for example, have autofocus, we can say, let's autofocus all of the sensor heads all at once now. Here's another image of the setup. In this case, we have all the sensors connected together to a controller and a DAC. So it's using both functions. That's kind of the hardware that I was talking about, the controller box there. And then here's another view of a bunch of the systems on the MDE. Yeah, so it's pretty flexible to set up. The nice thing is that we can potentially create a fixture for whatever the measurement requires, or anybody else can create a fixture, or the sensor heads can even be mounted on something else, a railing, or wherever they may need to be mounted. Pretty flexible in that way. As I mentioned, we can use pretty much any type of Polytech single point LDV in this system. And the nice thing is that we can even mix and match. So we can use, say, some VibraGos and then maybe also some VibraFlex systems. So if you already have one or two of them and you want to add another one, that's totally possible. We have the VibraGo systems, the VibraFlex systems, long range systems, industrial IVS systems, compact systems for microscope use, or even just macroscopic use as well, and high-speed systems as well. The single point vibrometers that we have, kind of like I mentioned on the last slide, are the VibraFlex series. Those include the long range Q-Tech, differential, lots of different options there. And then we also have the VibraGo system and the industrial vibration sensor as well, the IVS. With this combination, we can go up to 24 megahertz and 30 meters per second in terms of sensor head sensing. And we have options across the board for Q-Tech with infrared or helium neon. Basically anything that there is, it can be combined into an MDE system. So talking about some configuration options, the system doesn't require that we use it as the data acquisition. So some people might have their own data acquisition system. In that case, the MDE could still be useful because, like I mentioned, it can control all of the sensors at the same time. That means that not only can it autofocus all the sensors at the same time, but it can also adjust their sensitivity and just make it really convenient to do all that instead of going to, in this case, all of the VibraGo systems and tapping on each one of their touch screens individually to change the settings or autofocus. That can all be done remotely just by one click on the computer. So it makes it really convenient. It's great to be able to do that. In addition, though, the MDE system also has data acquisition options, and there it just creates an all-in-one system so that not only can you control the sensor heads, but you can also record from them straight to disk as well. We also have the option to define geometry because, as you can imagine, it might be useful to create a predefined geometry of the points if you want to take those points and do some kind of analysis, like modal analysis with them. Then having the geometry is quite important and knowing which sensor was measuring where on the given object. Here I'll talk about the components a little bit more. So we are going to need a computer. A computer is going to be required in any case to interface with this system. We have the ports that connect to the sensor heads. So Ethernet for control or data acquisition, or for some of the systems, BNC data acquisition as well. We also have some storage for just keeping the systems inside of the rack when they're not being used. An overview of the software is here. So we can see the data acquisition if that feature is selected up at the top, and that'll show a live view of some of the recorded channels, whatever recorded channels you want to look at. Then down below, we can see that we can group the vibrometers into subsets of 8, and then we can see all of their signal levels, all of their current settings, and all of their controls all at the same time. So to select how we would want to make our configuration, it's all going to be up to the given application. So how many sensors do we need? What spatial resolution do we need? Right. So that'll determine the number of sensors that are required. What sensor? That's going to be determined by something like bandwidth, maximum velocity. Do we need to measure through water, for example? So then helium neon would be an option there. Lots of different things that could affect the configuration of what kind of sensors are needed. Even, do you already have some sensors? That could be another determining factor. Bandwidth, yeah. So what bandwidth is required on the data acquisition side? That would be not on the sensor side, but in the system itself. We can select different data acquisition systems in there so that we can measure up to different bandwidths for the given application. What do we want? Do we want only control? Do we want control plus DAC? Or do we want geometry as well? So all of those options are available in the configuration of an MDE system? And then finally, do we need any accessories? Do we need to interface with the camera so that we have the camera as a reference for later on, not only potentially for positioning the lasers, but also for knowing where exactly on the object the lasers we're measuring? Do we want a rack mount? Do we need a geometry scanner to get the geometry? And then do we need to have post-processing capability? Talk about some application examples. So yeah, here we can see an animation of a golf club. You can see all of the points from a bunch of measurement locations. In this case, it was 24 systems measuring simultaneously, pointed at different locations on this golf club. And this result that we can see is a time domain animation. So we see the initial impact, and then that impact travels through the length of the shaft, and there it goes. Yeah, we can see the entire time domain history of every single point. That'll let us derive things like wave speed in a medium, or a lot of different things. Could be used for crack detection, or the sky's the limit. We can also look at the frequency domain and then see the different deflection shapes. This might be useful if we want to do something like modal analysis so that we can update models, or even just look at where energy might be concentrated in a system. Here's an example of a wine glass. So here the points were measured around the wine glass from different angles of incidence. This kind of measurement, for example, wouldn't be possible in one shot with the scanning system because we have measurements from sides, from the front, from the back, and yeah, we can't measure them all at the same time. So that makes the multi-point MDE system have an advantage because we can just ping the glass one time and then get the full data set all at once with essentially no post-processing time. Once the data is collected, we can visualize it more or less instantly. There's no additional post-processing required. Here is an example of a setup on a rifle. So this is a unique application because what we can do is we can measure the response of the rifle and then also see the impact of the bullet and get the time delta there. That'll tell us about a lot of different things. We can derive even the bullet speed from that. I talked about sensitive applications before. So something that maybe we don't want to impact multiple times because it would risk causing damage to the device under test. So in this case, we have a painting, and potentially we would want to look at how does that painting respond to vibration, or how does the painting in a fixture respond to vibration? Why that might be important is because, let's say we want to transport a painting, we want to make sure that we have a box for it that's designed in such a way that it minimizes vibration on the painting. Well, how do we test that? We would need to excite the painting, but we don't want to do that too many times for a priceless painting because, well, yeah, obviously we don't want to just shake a nice piece of art a bunch of times. So this gives us a way to just excite it one time and get a full result from that one excitation. Here is an example of a symbol, and we can see the resulting deflection shapes from just a single impact over on the right. Those are all contained in just one data set. So we can take our cursor and move through the spectrum and look at the 22 hertz signal, the 38 hertz signal, or the 95 hertz signal. It's all in there. It's just place your cursor here, here, or there, and then get the animation as a result. Here's another unique example of something that we were able to do using a multi-point system. We had 4 sensors mounted on a fixture, on a custom fixture, and we used some camera systems as well as the sensors at very specific orientations to measure strain. So talking about strain a little bit, we can do two different things. We can map the strain across an object using our 3D system. So with a 3D system, if we run an excitation for a device under test at, let's say, a given frequency, maybe 5 kilohertz or something like that, as an example, we run the excitation at 5 kilohertz and we quickly move the 3D sensors across the surface and map it all out. That will give us the displacements of all of the given points on the surface. Since we can also get the geometry of the surface, we can get the distances between the given points. And because it's a 3D measurement, we can get the in-plane displacements. Then we can get we can take the respective displacements of points next to each other with a known geometry, and then we can calculate the in-plane strain from the displacement as a result, delta L over L, for any given combination of points on the surface, neighboring points. And then that allows us to get a strain map across the surface. But the thing is, in this case, that this is just an excitation at a single frequency, and it doesn't monitor the strain. It just maps out the strain at a given frequency. So what if we have something where we want to monitor strain over many, many cycles? Some people in materials testing do high cycle or very high cycle fatigue testing, where they take the specimen, the strain specimen, and push it, pull it, push it, pull it, and they just do that a bunch of times over and over again until they see that it wears out. And they want to potentially monitor that over a long time. Well, classically, you can do that with a strain gauge just by attaching a strain gauge to the point of interest on the material specimen. But what if you also want to heat up the sample at the same time to see how that affects the test? A strain gauge probably won't survive that. Or what if the number of the number of cycles is so high that the sample itself outlives the lifetime of the strain gauge? That also will cause problems and make the test not possible to do with the strain gauge. It's also possible that because so many cycles are required to do this testing, that the strain that in order to do the testing in any reasonable amount of time, very high frequencies are required. Those frequencies might also not be compatible with the strain gauge that would be used. So in all of those cases, having a laser system that can simulate a strain gauge could be beneficial. In the setup that I showed in the previous slide, 2 slides ago, we had 4 single point systems connected in an MDE configuration. So 2 of them were pointed at one given point, the other 2 at another. And by knowing the distance between the 2 points, that we were able to monitor strain on a strain sample this way. All right, talking about some other types of applications. Here is a bridge, and potentially we would want to monitor different things in the bridge. So we could connect multiple long-range sensors all together in an MDE configuration in order to measure different points on the bridge as it sways, and potentially also on the cables themselves to measure tension. Here's another example of a multi-point. Well, actually, in this case, the example that you're seeing is a scanned measurement, but it required the subject to hold extremely still over the course of minutes. That might not always be possible. So in that case, a multi-point measurement could be beneficial for things like haptics testing or medical applications as well. Then in terms of post-processing the data, we can pretty much do anything. We can export the data to UFF, text, CSV. And then from there, we can use even our own post-processing tools. We have a native one. We can use pretty much any software tool we can think of to do post-processing. Yeah, etc. There, you can do anything with that at that point because you get the raw data. One example of post-processing would be for, let's say, modal analysis by using a tool like ANSYS to compare the vibrational results to a simulation, and then in that way update models. All right. Well, thank you everybody for joining. If you have questions, please let me know. But it's been a pleasure talking to you, and I hope you have a great rest of your day. Thank you.